he will present now the continuous formulation of this very famous Kuramoto model. So, and we have a small announcement to do. There has been some small change again in the program. So now, we thought that it could be interesting for those presenting posters and also for those students who don't present anything. If you want, we were thinking about making a session of flash talk sessions. The objective could be present your poster saying, okay, guys, I'm Mario Chavez, I have a poster on this topic, I'm working on this field, my interest is this, and I have a poster. Or if you don't have any presentation, you can present yourself, present your interest, and making, okay, I'm here, guys, I'm interested in this topic or not. So today, instead of the hands-on, you can present a 5-minute flash talk that can be done tomorrow, that will be done tomorrow. So the flash talk will be done tomorrow instead of one of the hands-on or workshop or whatever is the name. Oh, today you can prepare it, and tomorrow will be this presentation. Please organize. We are not 500, so we can organize, but let me know, or Hilda or Jesus, let us know who are interested, only in order to do a list and to organize the presentation to see if we need 1 hour, 2 hours, I don't know. So the objective, again, is only a flash talk for saying your name, a small presentation, what you do, what you are interested in, and probably if you are looking for a postdoc, a thesis, or I don't know. Okay? And now, Jesus, please.
Yeah, don't be shy. I mean, it's very informal, as Mario says, so, I mean, we invite you to do this. Okay, so now we are going to continue with the last part of the first lesson. You remember that yesterday we have to cut in 1 hour because of the IFT colloquium. And what we are going to do, as Mario said, is to introduce a formulation, which is called the continuous formulation, which will allow us to solve, again, the Kuramoto model, especially the critical coupling of the Kuramoto model, in a very different way as we did, okay? Let's remember the Kuramoto model. We have a collection of phase oscillators, our fireflies, okay? So we have a collection of n oscillators, n being very large, okay? And this is the equation. So we have the phase, we have the evolution of the phase, we have the natural frequency, which in principle is different for each oscillator, and you draw this frequency from this frequency distribution that typically, remember, is an unimodal distribution, typically centered at omega equal to 0, even, etc. And then you have the coupling, which is the important term because it's nonlinear and takes into account all the contributions of all the nodes in the ensemble, okay? Because remember that in the Kuramoto model, in the original Kuramoto model, there is an all-to-all coupling, okay? Each oscillator sees everyone. Okay? And the coupling is the typical one, so it's the sign of the phase difference between a neighbor and the node itself, and the strength is weighted by this K. Okay? This K is our control parameter that played a similar role as A in those models that were very, very simple. Okay, so this is the typical synchronization transition as a function of K. We go from the unsynchronized solution in which all the oscillators are pacing at their own natural frequency, so they fill the circle, and as we increment K, there is a cloud of synchronization which is formed, and all the oscillators start to be incorporated in this cloud, and this cloud becomes very narrow and localized as K increases, okay? And in order to monitor this transition, we introduce the Kuramoto order parameter, which is just the sum of the phasors associated to each of the nodes, obviously associated to the angle of each oscillator, and we take the sum of this phasor, we take the average of this phasor, and we get a complex number whose modulus, these R, tell us if the system is synchronized or not, okay? So R equal to 0 means that this situation, so there is complete incoherence, and R equal to 1 is a full synchronized state in which all the oscillators, okay, get into the same position of the unit circle, okay? So the cloud is narrow. And we were interested in this point because the important thing here is that synchronization does not emerge as soon as K is larger than 0. We have to wait until a critical value, which is this synchronization coupling, this critical synchronization coupling, in order that the incoherent solution, the non-synchronized state, becomes unstable, and the synchronized solution starts to emerge, okay? And this is something we did yesterday. We put the Kuramoto model in this form, okay, which is just a simple transformation in which the mean field character becomes obvious, as Strogatz says in his famous article. And then with this equation that remember as all these equations that we checked yesterday in the beginning of the lesson, we could divide the population into lock or synchronized oscillators and those that are drifting, those lock that are incorporated in the synchronization cloud, and those drifting that are outside the synchronization cloud. And with this distinction, we could make some operations with the Kuramoto order parameter, and we reach to this value, which is the critical coupling. And this was the final result of the lesson yesterday, right? Which is, if you want to start observing a synchronized state, or the first synchronized state, you need to reach a critical coupling, which is 2 divided by pi and divided by this G0, which is the fraction of oscillators that are pacing, whose natural frequency is the mean frequency of the ensemble, okay? So they are already pacing because the natural rhythm is just the synchronization frequency, okay? If you have, remember, a very peak distribution, so a very peak G omega, then this number is very large, so the critical coupling is very small. If you have a very broad and width distribution, this number is very small, and then the critical coupling, the coupling that you need to reach is very large. Okay, so we keep this result here, and let's do another approach. When we have this kind of equations, we assume that this is one equation for each oscillator, okay? And we assume that if we have n oscillators, we have n equations, okay? But if n is too large, we can lose the track of the index of the oscillator and start to work with all the oscillators having a given natural frequency, okay? And then we remove the index, the label, I, and we consider that this is the equation for those oscillators whose natural frequency is omega, okay? And this is the typical equation for these oscillators. How many oscillators of this kind you have in your network? Okay, you know G omega, okay? But we are going to work with another quantity, which is the oscillator density functional that I have written this way, which is for each natural frequency, we have the density of oscillators that at a given time t are located at some angle theta, okay? And this is the oscillator density functional, okay? If we know this, okay, if we know this, we know everything, because we can calculate the Kuramoto order parameter, because it's just to average, just to integrate, sorry, across all the angles and also across all the frequencies, and you have the Kuramoto order parameter. But the thing is that we need to know which equation to obey this density functional, okay? So for this, imagine that you have this situation, and we can distinguish one color. Okay, imagine that we focus on one color, and that the density of the oscillators with one single frequency is this one, okay? So here you have a little bit more than here you have also an accumulation, here you have something here. I mean, it's not homogeneous, okay? Then this is something that happened for some time t. I mean, you take a snapshot of your system and calculate this density, and you obtain this curve, okay? Now the question is this stationary? And if not, which is the differential equation, which is the time evolution of this quantity as a function of time, okay? So in order to do this density functional obey what is called the continuity equation, which for you, that if you have studied fluid dynamics, for instance, is very obvious. But I don't find it obvious, especially for those that are not very familiar with fluid dynamics. So let's derive what is the continuity equation. So focus on a piece of the unit circle, like this. So we have spanning the area between theta and theta plus delta theta, okay? And the number of oscillators in this region, if we have this quantity, is this one, okay? This is the number of oscillators between theta and theta plus delta theta for some time t, which is the density, okay, at a given theta times the width of this region, okay? Delta theta obviously is very small, okay? This is an infinitesimal calculus, okay? And I want to know this one, which will be what will be the quantity of oscillators associated to some natural frequency omega that are between theta and theta plus delta theta, but in the next time step, okay? So in t plus delta t. Okay, what we do? Well, this quantity and this quantity must be different because there is some inflow of oscillators from here and some outflow, okay? Let's compute the inflow. The inflow will be the oscillators that you have here times the velocity times delta t, because it's the period of time you are counting between t and, I mean, it's the width of the period of time, okay? So this is the inflow. And the outflow is the number of oscillators we have there, here, so in theta plus delta t, here, times the velocity at this point. Remember that the velocity, we have it here for this and for this. You can calculate from this equation, times delta t, okay? So at the end, what you can write is this equation. The new number of oscillators is the old one plus the inflow and minus the outflow. That's all, okay? Let me pass this quantity to the other side. And let's divide it, because this should be invariant for any delta t and any delta theta, okay? This should be valid for any choice. So let's divide by these two quantities. And then you can cancel out this, and you notice that this is the derivative, the time derivative of the density, okay? The partial derivative, because t, the time is one variable. And here, what you have is the derivative with respect to theta of a quantity which is the product of the velocity and the density, okay? Minus, in fact, okay? And this is the so-called continuity equation for the oscillator density functional. This, sorry.
You showed us yesterday that in some cases you have this phase lock that trap all the solutions in one point.
We will reach this point.
That won't be valid. It won't be a good argument, because you won't have a continuous flow anymore in all the regions in phase.
Yeah, in this case, the solution is special, but we will reach this point later, okay? We assume that now is the most general situation. Then we will have to distinguish between this case, which is the lock solution, and the unlock solution, or the drifting oscillators, okay? Yeah, we will reach this in two slides, okay? This is how to derive the general equation for this quantity, which is what we want to calculate, okay? Because I repeat, if we have this, then we have the Kuramoto order parameter, okay? And we will do this. Okay, so in fact, this is the calculation of the Kuramoto order parameter. As I said 5 minutes ago, you take this, if you know it, obviously, you take the phasor associated to this theta, you integrate across all the possible angles, and obviously weighted by the frequency distribution, you integrate across all the possible frequencies, and you have the Kuramoto order parameter, and that's all. You only need to know this, and this is the difficult part, okay? Okay, so we seek for stationary solutions of these equations. We need stationary distributions in which this is equal to 0, okay? In order to this being equal to 0, we have a solution which is obvious, which is the uniform distribution. If you plug this distribution in the former equations, you will realize that this is a solution of this equation, of the first equation, but obviously this is the equation associated to R equal to 0, which is always valid, but obviously this is the trivial one, okay? We need to go beyond the incoherent solution and find the non-trivial solutions associated to this density. Okay, the non-trivial solution need that this derivative is equal to 0. So this quantity cannot depend on theta. Okay, remember that here omega is a parameter. Omega is just a level of the oscillator. So we need that this product, remember that this theta dot is this equation, okay? This theta dot times the distribution we are seeking for should be equal to a constant, or something depending on omega, but not depending on theta, okay? And then here we have two possible solutions, okay? For those oscillators that are drifting, okay, so so that the omega, the absolute value of the omega is larger than kr, so this equation cannot be equal to 0, okay? This equation, the steady state solution, is not valid anymore because these are the drifting oscillators. What we have is that this rho should be 1 divided by theta dot, and theta dot is this one, okay? This way is the only way to satisfy that this is a constant. But, as we were discussing before, for those oscillators that are locked and they are fixed, since this is 0, because they are locked by definition, the only distribution which is possible is a delta de Dirac, okay? Obviously localized in a singular point, okay? So it's not a typical function, it's a distribution, okay? And we have to treat them with care, so to say. Okay, obviously the theta associated to each omega changes, and for one omega I have a particular theta that corresponds to the log solution of the oscillators, okay? So we have this unlocked distribution, these locked distributions, and we have to operate. Here, I have just put the normalization, and let's operate with it in order to calculate the Kuramoto order parameter. Okay, let's start with the unlock solution. So we can calculate the Kuramoto order parameter for the unlock oscillator and that for lock oscillators. And this is the integral we have for the unlock oscillator. Obviously, we have now that the frequencies go from kr to infinity and to minus kr to minus infinity, okay? Because they are unlocked. Here we have the frequency distribution, obviously. Here we have this solution, this one, and here we have the phasor associated to the oscillator. Okay, so here we have pay attention. Instead of plugging this into this integral, we have to pay attention to symmetries, okay? And there are very nice, we know that G omega is even distribution, so G omega is equal to G minus omega. This is by definition. And if we look to this particular distribution that we have derived before, we notice that this symmetry happens. I think that Albert told about this symmetry yesterday, maybe, or something related to this symmetry. It means that if you put here minus omega and change theta by theta plus pi, then you will find the same solution as if you put omega and theta, okay? For those oscillators that are, remember that here we are, integrating between kr to infinity and minus kr to minus infinity. So if you are in an omega here and here in a minus omega, so this is the symmetric omega, then what you find is that rho at theta here is the same as rho at theta plus p here. These two quantities are equal, okay? This is the symmetry. You see, okay, what else? The thing is that here you have cosines and sines, and the cosine of theta plus p is minus the cosine of theta, and also the sine of theta plus pi is minus the sine of theta. So, because of these symmetries, it's easy to check that this is equal to 0, okay? And this is obvious because it's the Kuramoto order parameter for the unlock solution, okay? Okay, so this is ruled out. Let's focus on what happened for the lock, for the Kuramoto order parameter corresponding to lock solutions. And what we find is, again, the definition of R. Now we are, again, studying this region, because these are for lock oscillators, remember. And the integral is the same, with the exception that here we have the Dirac delta. So we plug it into the integral, and then we have this theta associated to the log solution. Obviously, this exponential is a complex number with sine and cosine. We know that the sine is not surviving anymore, and we have the cosine, okay? So this is the final integral after making the change of variable between omega and theta that we have to calculate. And this is the very same integral as we had yesterday, the very same integral. If you remember and you go to the previous lesson, you will check, you will see that this was the very same integral. We have the trivial solution, R equal to 0, and we can calculate the critical coupling by taking this limit, R going to 0, putting R0 here. We have this integral, solve it, and then we have this equation, which is, if you see this, the very same equation as we had yesterday, okay? So the critical coupling is 2 divided by P, and this is the contribution of the number of the fraction, better, of oscillators that are already pacing to the mean frequency, okay? And this is what happened at the onset. We can go beyond, and we can go also in the integral, in the former integral, and instead of taking only the 0-order approximation, which is G0, G equal evaluated at 0, we can go in other orders. And if you go in other orders, you can also, we are not going to do it because, I mean, well, it can be a homework because it's nice. We can have this evolution, okay, that again, you see that the trend that the Kuramoto order parameter obeys close to the bifurcation point, close to the onset of synchronization, go with the square root of the coupling minus the critical coupling. So the very same relation as we found in the saddle node bifurcation, if you remember, when we approach the bifurcation for a single oscillator. So it's the very, very same behavior, okay? Why here is the second derivative of G? Why is not the first derivative? Because when you make the expansion, you will take the 0 order that goes with G0. The first order will go to this, but this is equal to 0, but because remember that this is a function with a maximum at 0. So you have to go to the next order in order to have non-trivial results, and that's why you have to you have this the expression of the second, the evaluation of the second derivative of J at 0, okay? But this is something that goes beyond the scope. Okay, any question up to now? No? Okay, so now we have finished the presentation of the Kuramoto model, and now we are going to pass to a different situation in which we don't have an all-to-all coupling, but we have a network, okay? And let's study what happened in the Kuramoto model on a network. Yesterday, someone asked, okay, but if the connectivity of the nodes is not all the other nodes, but more or less a big quantity, what happens? And I say, okay, then the Kuramoto model is almost valid. Here, when you have networks, look that the average degree, which is this number, is much larger than n. Okay, for instance, here you have the C. elegans brain, so to say, this is the C. elegans neuronal network, which is very small, but you have almost 300 neurons, and the average degree is 8. Okay, it's 2 orders of magnitude less of the size. Okay, and this is what characterizes networks. Okay, the typical number of connections is order of magnitude lower than the size of the network. Okay, and remember that in an all-to-all coupling, the connectivity of a node is n-1, so it's the size of the network in effectively. So it's a very, very different scenario, and that's why we are going to do a lot of approximations. Okay, so for what's coming now, forget about being rigorous. Okay, there are no exact results, in fact, and I want you to realize about the kind of approximations we are going to make it sequentially. So my goal today is not that you become experts in calculating things in network, but that you realize which are the approximations that are behind the expressions that we are using. Okay? Okay. So this is the start of the second lesson. Okay, half an hour, perfect timing. And this is the menu, okay? Again, because we have this delay, I'm almost sure that this part will be covered tomorrow, okay? Don't worry, I mean, we are perfectly in time, but this part, I think, or at least one part of this final part will be covered tomorrow. So we will start by this, the appetizer will be what happened in a network, what is a network, why we study the network, and what happened when you put numerically, which is something that you can do on your computer, a Kuramoto model in a complex network. Then we will study, and this is the central core today, of how we can derive the critical coupling, okay, but in a network topology, okay? So we will make use of techniques which are similar to those that we have seen in the Kuramoto model in order to derive the new critical coupling. And then finally, we will cover what happened when I have learned a lot about how a structure influences dynamics so that I can study dynamics to infer which structure is behind my network. Imagine that you don't know the structure. You only see the dynamics. This is what happened in the brain. You don't know. You don't have the wiring typically. You have the dynamics. You have the correlations between the dynamics of each area. How can we use the dynamics, the observation, in order to infer something about the topology, okay? And there are many studies about it. I will cover only one piece, which is related to modular networks, and we will see what happened. And finally, once we have going from a structure to dynamics and from dynamics to structure, what we are going is to couple structure and dynamics. What happens when a structure is influenced by dynamics, and here we will talk about two topics: adaptive networks, okay, a little bit, and explosive synchronization, okay, which is the result of coupling topology and dynamics, okay? So it's a very big menu for today and also for tomorrow. Okay, so let's start with the Kuramoto modeling complex network. Okay, we have a network like this, okay? And a network is nothing more, nothing less than a collection of n nodes. For us, the nodes are the oscillators, obviously, and L links, okay? The number of links, you know, is much less than the maximum possible number of links, which are n/2. This is the maximum possible number of links that you can have in a network, which is the combination of n nodes in pairs. So this number typically is much, much, much smaller than this one, okay? And a network can be expressed in many different ways, but the typical way is the adjacency matrix. The adjacency matrix that tells you, for instance, here, A21 is the strength of the connections of node 2 with node 1, okay? We will assume that we have a directed network, so this network is symmetric. So if I'm connected to Albert, Albert is connected with me, okay? And we will also consider the simplest scenario in which these numbers are binary, okay? Are either 1 or 0, okay? If you are connected to somebody, you have a 1 in this entry. If you are not connected with this person, you have a 0. So this is a binary matrix, symmetric matrix, n times n matrix, okay? And this is the adjacency matrix. Okay. Once you have a network, okay, then you can write the Kuramoto model in a network. This is the version, okay, the generalization of the Kuramoto model in a network. And look that here you have this object, which is the adjacency matrix. Typically, we write the sum across all the nodes. So we continue to write j going from 1 to n, and this is like a filter, okay? If j is not a neighbor of I, then this is 0, so this term does not add to the summatory, okay? On the other hand, if I and j are neighbor, this is a 1, and then you have the typical coupling of the Kuramoto model. Nothing less, nothing more, okay? And lambda now is our control parameter, the strength of the coupling, plays the role of A and K in the former models, in the former equations that we have derived. It's not normalized, yes, but you can normalize. I mean, you can, and then it's just a change of scale, okay? It's not important. Why it's not normalized? Look, networks, K typically does not grow with n, okay? So in the Kuramoto model, the larger n, the larger the number of terms you have here. So you have to put a normalization. Here is not necessary, okay? Because you have a limited growth. But if you want divide by n, it's just a simple change of a scale. So you can do it, okay? There's no problem. You can say, okay, this is k divided by n. Then you have a different normalization. This is Albert is laughing because it took years of fighting with people because of this question. So if you put lambda divided by k sub I, okay, then you are using a different normalization for each node. And then, yeah, this is a different situation, okay? And it corresponds to something that I don't want to discuss, is the paradox of heterogeneity. You find different results, et cetera, but here we are not going to discuss about it. But this is a very important question, very relevant point. Any other question? Well, it's normalized. I mean, if you define lambda as k divided by n, so it's the same. Okay. Lambda, okay. The typical numbers will be smaller if you want, okay, for lambda, because, but let's see what happens. We will be able to compare with the Kuramoto model, don't worry, and you will see what happened, how they are related with the critical coupling, okay? So numerically, you can do it, and mathematically, we will compare the critical coupling of the Kuramoto model with the new critical coupling associated to this, and we will do it, so you can check it, okay? Okay, so we have this object, as I said, is like a filter that tells you if you are a neighbor, then you have a coupling. If you are not a neighbor, this is 0, and then this term does not enter into the summatory. And let's see what happened. Okay, in order to see what happened, we have to define, again, the order parameter that tells you the degree of synchronization of your network. The order parameter is the same. Exactly the same. It's just the sum over all the nodes of the phasors associated to each node, and then divided by n because it's the average. And this is a complex number with a modulus R, which is the degree of synchronization, and a phase, and the average phase of the system. It's the very same. Nothing changes. Okay? Okay. And then we have to study typical network structures. Okay? For this, you can do two things. You can take a real network, for instance, the brain connectome or the power grid or whatever network you have. Then construct the network, take the network, decode the network, encode it in the adjacency matrix, and study what are the properties of your network, okay, before studying what happened with synchronization. Or you construct a network from scratch by using the multiple models you have already in the literature, okay? How many of you know about the Barabasi-Albert model, for instance? Okay, not that bad, okay. Barabasi-Albert model, Erdős-Rényi random geometric graph. I mean, there is a family of models that allow you to construct synthetic networks, so you can do it in your own computer without the need of taking data. Obviously, these networks are simpler than real networks. Real networks have a lot of characteristics that are complex, okay? In any case, when you have a network, you have to describe the network. And one of the typical, this is not a course on networks, so don't worry, but one of the typical things you look when you have a network is the degree distribution, okay? The degree distribution is just the probability, measures the probability that if I take a node at random from a network, this node is connected to k neighbors, so it has degree k, okay? Being connected to k neighbors means having degree k. We call it degree, okay? So, for instance, imagine that you have a network and you have this degree distribution. This degree distribution, it's an unimodal distribution, has a well-defined mean, and you can say that not all the nodes have the same number of neighbors. But if I tell you the nodes have this number of neighbors, I'm not lying you a lot, okay? Because more or less, the connectivity of the nodes is always very, very close to the average one, okay? This is, for instance, what happened with random graphs, with Erdős-Rényi graphs, which are the typical graphs used in graph theory in the last century as the prototypic networks in which you can construct it from scratch very easily. I mean, you consider a set of n nodes and consider each pair of nodes, and with some probability p, you make a link. And obviously, with probability 1 minus p, you don't make a link. And that's all. I mean, this is 2 lines of codes in order to generate an Erdős ranging network. And if you do this, then the distribution is a Poisson one, which is not symmetric, but has a well-defined mean, etc., etc. The problem is that when you go out and check networks in the real life, the degree distributions are this way, okay? Have heavy tails. These heavy tails means that there are a lot of nodes that have a degree which is orders of magnitude larger than this quantity. So in principle, you can have 2 networks with the very same number of nodes, with the very same number of links, which means that they all have the very same mean connectivity, but they are very different because one is homogeneous, and the other one is completely heterogeneous, okay? Heterogeneous means that, yes, you have a well-defined mean connectivity, but the problem is that this connectivity is meaningless. And meaningless means that, yes, it's a number, but a lot of nodes have a connectivity which is much, much, much larger than this average connectivity. Then, in this case, if for this network, if I tell you that the nodes have a connectivity, typically this one, then I'm lying a lot, okay? Because this mean connectivity is not meaningful, okay? That's why, well, it's because of mathematical transformation, but you can say that that's why these networks are called scale-free, because the scale, the average degree, is not there. I mean, it's a number, but it's not meaningful. And a typical example of scale-free networks are those in which the degree distribution is a power law, okay? And in a power law like this, and you see that this is a log-log plot, this is a linear plot, this is a log-log plot, you find this nice linear relation in log-log plot in which the slope is related to this exponent minus gamma. When gamma is very small, 2, 3, between this range, this means that this network is very heterogeneous, okay? The tails are very heavy. If gamma is large, 6, 7, whatever, then, okay, it's a power law, but the network is not heterogeneous anymore, okay? So this exponent measures the heterogeneity of the network. The smaller, the more heterogeneous it is, okay? Because this goes to a range of several orders of magnitude. Here you have it. This network, the network that corresponds to this degree distribution, have an average degree of 6. And look that there are nodes whose connectivity is close to 1,000, okay? And this is what happened. Huh? This is the problem with real networks, okay? Any question about this? This is the final part of the network introduction, okay? Nothing more, nothing less. Okay, let's put a network, an homogeneous network and an heterogeneous network, an Erdős ranging network and a scale-free network in the Kuramoto model. So I take the network, I encode it into the adjacency matrix, and I put the adjacency matrix into the equation. What happens with the typical synchronization diagram? This. What happened is that the onset of synchronization is anticipated in the case of heterogeneous networks. So the numerical result was that heterogeneous network anticipate the onset, favor the onset of a synchronized cluster, okay? And this was observed at the beginning of the century when scale-free networks were discovered and discovered and discovered. So it was, again, a reason, a dynamical reason in this case, to study networks, okay? Because it seems that they are special also in terms of synchronizability, okay? Okay, if you go and study different scale-free networks with different gamma, remember this is the most heterogeneous case, you will see that the most heterogeneous case anticipates more than other values of gamma, like 3.6 or 6.4, in which the synchronization is not so anticipated. So scale-free networks anticipate synchronization, and the more heterogeneous they are, the more anticipated is the onset of synchronization, okay? Okay. Can we do something? These are numerics. Can we try to understand what's happening here, how this topology, how the heterogeneity of the network alters the value of the critical coupling? Remember that the critical coupling we have derived so far, this is the Kuramoto model, was this one. Which form has the new one, okay? And we will compare with the former case. Okay, So now we enter into how to study synchronization in complex networks. Okay, this is our problem, and I'm going to define, well, there are different approaches in order to address this question. What's the influence of the network structure, encoded by matrix A, in the synchronization transition? If I have A, if I have the network, can I derive the critical onset, the critical coupling for synchronization, and can I derive how the Kuramoto order parameter evolves with the coupling? This is the main question. And the problem is that it's not as simple as in the mean field Kuramoto model. Why? Because we have lost the mean field character of the equations. Look at this. This is a summatory. In the original Kuramoto model, this sum goes from 1 to n, and all the nodes contributed to the sum. Now, because we have this, and the problem is that the number of neighbors is much, much smaller than the size of the network, you cannot speak about an average behavior in your neighborhood. Your neighborhood is not an average of the system anymore. Your neighborhood is your neighborhood, and that's all. Okay? It's not, or should not be, in principle, representative of the overall state of the system. And that's the problem, okay, we have in the case of networks. Okay, there are different approaches, okay? There is in 2004, Ichinomiya introduced the continuum limit approach. Remember, is the first part of the class. So what he did is to generalize what we have done, okay, and derive a density of oscillators adding a new level, okay? We have a level for oscillators that was the natural frequency. Now we have a second level for each oscillator, which is also a constant thing, a property of the oscillator, which is the number of neighbors, k. So an oscillator is defined by the natural frequency, and the number of neighbors is associated to, okay? So we can construct this kind of density functions in which we have, which is the probability of finding an oscillator with natural frequency omega and degree k in or placed at theta at time t, okay? And with this, again, you can ask for the equations, ask for how is the shape associated to these densities, and construct with the help of g omega, and in this case, the help of the degree distribution, because this is the new ingredient we have to take into account, which is the shape of R. Okay? And the mathematics are pretty similar what we have done at the beginning of the class, but with the exception that we have k, and we have to work also with the degree distribution, okay? I don't want to bother you with, again, the same or typically the same mathematics, so we are not going to tackle this. We are going to tackle another theory which was presented 1 year later by Restrepo, Hunt, and Edward Ott, which is the time average theory, which is very nice, in which we take time average approximation, okay? But the thing is that we will be able to connect this theory with the theory developed by Ichinomiya, okay? And we will see how it works, okay? So let's start by looking to the time average theory, which is the one I'm interested in showing you. Okay, this is the local order parameter. And this is something which is the central ingredient of the theory. Look at it for a while. It has the form of the Kuramoto order parameter, right? You have a sum. Here is a complex number, the modulus, the phase, and here is the sum. And look, is the average, it's a kind of synchronization degree, not an average, the synchronization degree of the neighbors of I. Is not the synchronization of I with the neighbors, okay? I'm taking I, I'm taking all the neighbors of I, I'm forgetting about I, and I'm considering them and measure what happened between them, okay? If they are all synchronized, this sum, okay, this sum will be constructive because the phases will be aligned. If they are not synchronized, this sum will be destructive, okay? Also important is that they take the time average, okay? This is not an instant, this doesn't depend on t, okay? Well, this depends on t, but it means that this is done for a time window, let's say between t and t plus capital T. So the capital T is the number of time steps I use to make the time average, okay? Remember, we are doing the time average approximation. Yes?
Sorry for being nasty, but what if the average of time is not meaningful?
That you are, I mean, pues, in this case, you are, no, I don't want to say the word. I'm thinking, I get it. I mean, if the time, in fact, the time average now, we will remove it, okay? In order to, and you will see in which cases we can do this removal and in which cases we cannot do it. It's the first approximation. But yes, if the time average, you cannot do it because it's not meaningful. Exactly, and it depends a lot on how you make the average, so you don't have a constant one. I mean, this is, I mean, this is the price you have to pay in order to make calculations. Yes? No. There is no degree missing, okay? This is my next point. I say it's a kind of average degree of synchronization. It's not an average because in order to be an average, you need to normalize by k sub I, okay? But it's not on purpose. In fact, consider that I want to use it in order to know how the network overall, not the neighborhood of I, but how the network overall is synchronized. And I'm not going to use it, but just to inform you, if you want to do this, you can define another global order parameter that measure all the sum of these ones and then divides, now yes, by the twice the number of links, which is the sum of the connectivities of the nodes. Because in this case, yes, the order parameter of synchronization of the overall network needs to be between 0 and 1, okay? But this is just the thing. By the way, I put it here tilde because this is an order parameter of the synchronization, but it's not the Kuramoto order parameter, it's not this one, okay? And who cares? What I need with an order parameter is something that tells me if something is synchronized or not, okay? But this is not this one, it's another one, okay? But forget it for a while. Yes? Large enough. Yeah. You put, if you do it numerically, you put your initial conditions, you wait for a transient, and then you make an average for a large enough t, but after a transient, okay? So you have reached some kind of dynamical stationary state in which you have dynamics, but everything doesn't change in principle, because if Carmen, as Carmen said, this is not guaranteed. I mean, depending on the system, depending on the network, can be done or not. I mean, here assuming that the time average is well defined, but you do this in this way. Okay. Any other doubt? Yes. Will cancel out. In the drifting case, yes. There is a feedback, but then you have a different model. I don't understand the question. We can discuss later if you want with the coffee break, okay? Because I have to move, and otherwise, but okay, maybe later when I separate the drifting regime and the lock regime, so the drifting oscillators in your neighborhood and those that are locked, maybe there is an answer there, okay, for you, okay? But if not, we can discuss later, okay? Okay, so this is our local order parameter, okay? You understand it, it's very important. It's a local one, different for each node, involves a time average, and has nothing to do with your synchronization with the neighborhood. It measures the synchronization in your neighborhood, okay? Then what I want, because, okay, Homer Simpson comes here again, say, okay, you have to find an equation which is of this kind, okay? Because if you have an equation of this kind, then we can do mathematics because we already are in safe grounds, okay? Okay, say, okay, I need something that remove the sum and change the sign by this lambda times the local order parameter, this one that I have defined, and I have here the difference of my phase and here a kind of average phase in my neighborhood. If I have an equation of this form, I can start doing calculations. The problem is that this is not true, okay? Okay, can I do it? Okay, let's try. I need, in order to remove, in order to compare this part with this part, I have to multiply the equation by the exponential of I minus ti, okay? This way, I'm proceeding, I'm making the things in the same fashion as I did in the previous models. And if I do this, okay, then I have this have the sinus and the cosine, etc. And then I have this, and I have a problem because this is a time average and this is not a time average. Okay? We have this problem, okay? So what I can do is say, okay, this is not this, clearly, this is not this, but I will assume it is. But adding a term which is the correction, okay? So I assume that this quantity is not this quantity, but this quantity is this quantity and a correction that I plug it into the equation because I want this, obviously, because otherwise I cannot do calculations. So here I have something which is this is what I want, and this is what I don't want. And which is the form of this? The form of this is this one. And the good news is that this is the time evolution of the difference of this phase and the mean value. And when you have a large number of oscillators, these differences between the mean scales with the square root of the number of the oscillators. While this term here, which is the sum, scales with n. So, in principle, if one thing scales with n and the other one scales with the square root of n, if n is large enough, I can remove this. I say, Jesus, come on. N being large enough means that the number of neighbors you have is very large. Yes, I know. I know. Yes. I'm not assuming. Otto Restrepo and Hunt assume. That's the point. That's the point. Well, when you have a very large number of oscillators, yes. Mm-hmm. Mm-hmm.
And analyze that small one and assume that it's the same as the infinity, but the large number.
Well, you can take those parts that are very largely connected. In fact, this will be true around those nodes that have a very large connectivity. And that's why this will be working in scale-free networks. That's that. But this is a spoiler. I don't want to enter into this detail, okay? because it's the way you can calculate it. You can remove, at the end, you have a problem with the frequencies because they are, I mean, it's not only that you have an heterogeneity in your neighborhood, it's that also that you have an heterogeneity in your natural frequencies. In order to remove this kind of heterogeneities, a natural way of doing it is making time average. That's the reason why they do it. And then you are left with the heterogeneity of the network, which is the real problem here, okay?
How do you define large enough in this case? Because I imagine that, okay, at first you can assume that, but after you're doing all the calculations, you have to have a method to define what's large enough.
I tell you why. Do the theory, do the numerics with some n. If it works, it's large enough. It's the way it works, okay? Okay, because obviously this is true for n going to infinity. And I say, this maybe is true in the Kuramoto model because n is very large. But here we are filtering the neighbors. So the number of terms in this sum is not very large. This is valid when you have a very highly connected nodes. So this sum has a lot of terms. And then yes, the two terms scales differently. And then you can apply the large size theory, okay? Okay, how many approximations do we have? I think 2, right? 2. Okay, will be more. Okay, then we have this equation, and we are now in safe hands because we have the typical equations we are used to solve. So we look for the, no. Okay, so we look for the steady state solution. This means this is equal to 0. If the steady state is fulfilled, this is the equation we have to solve. And this is only valid when for those oscillators whose natural frequency, the absolute value of the natural frequency, is less than this quantity. Nothing new because we are now in safe grounds because we have recovered, so to say, in a nasty way, yes, the typical equation that we are used to solve. Okay. So in this case, what we can do is to calculate the local order parameter. Then I put this phi here in the other side. Then I focus to calculate this. This is a constant value. Then I can put it inside the average because it's just a constant. And then we can split this sum into those terms that are fulfilling the locking condition and those terms that are not fulfilling the locking and the drifting oscillators, okay? Well, you have now these two separate contributions. So you have neighbors that are locked and you have neighbors that are drifting, okay? Okay, for those that are locked, I can change the time average by the value because this is a constant value, okay? So that's all. And for them, for the others, I remove it, okay? Because they are drifting, and again, the time average of a drifting oscillator is 0, okay? Because they are not locked, they are drifting, they are pacing at their own frequency, and in this case, this sum, if n is large enough, again, is equal to 0. So I have here this term. I want the real part, because remember that R is a real number, so at the end, I want the real part. And I'm not satisfied because this expression is not like this, so I multiply by this and this in both places. These are a constant number, so don't worry about it. And now I have this expression, which is in the very same shape, fashion as this one. So we have I, J, J, so we have the same index, okay? Okay, so now here we have cosine and sine. Here we have cosine and sine. Remember, we are in the drift for the locked oscillator, so we have the cosine, the sine, and the sine. This and this can be substituted by using this equation because I know what is the value of the sine, and obviously the cosine is the square root of 1 minus the sine to the square, here the sine, and I have to solve this equation. And in this equation, this second part is 0 because this is an odd function, remember, okay? This is the sum between a minus omega and an omega, and this is an odd function, so it's okay. And I am left with this. Okay, and I have a problem with this because I don't know which are the faces, the average faces around your neighbors. What can I do? I'm interested in the worst scenario, so the minimum value of lambda that is able to to satisfy this equation. So what's the worst case if I want the minimum value of lambda? Well, take the maximum value of the cosine. And the maximum value of the cosine is equal to 1, okay? Third approximation or fourth approximation, okay? And I have this equation, okay. And this is the result of the time average theory, because now you can solve this self-consistent equation, okay? Now, if you have the topology, the adjacency matrix here, and you have the set of natural frequencies, so if I give you the network, the adjacency matrix, and a vector with the natural frequency of the first, the second, the third, until then, you plug this information here, and you can numerically solve which is the value of each R. And with the value of each R, you can recover the degree of synchronization of the whole network, because remember that with each local synchronization value, we can construct the global order parameter. The problem is that this is something that you have to do numerically. But it's very easy, by the way. It's really easy, okay? You can program it, and you don't have to solve any equation, okay? Just give me the adjacency matrix, give me the set of frequency nodes, plug it into this equation, and that's all. It's an implicit solution, but, I mean, we have methods to do it. Okay, and this is the result. Let's do more approximations because, okay, this is nice, but this is numerical, and I don't have any insights. So this is the solution, but if I tell you what happens in networks that have an adjacency matrix corresponding to a very heterogeneous graph, I don't know. Let's do more approximations. What we can do now is to consider the frequency distribution approximation, because the problem in order to solve this sum is that I don't know which are the specific natural frequencies of my neighbors. So let's assume that my neighbors is a typical set of the nodes in a network, so they are well represented by the frequency distribution. Obviously, if you have to use the frequency distribution, it's because, again, n is very large, and this is not the case in a network. But assume that you can do this, so you can make this average across all the possible frequencies, obviously bounded in the set of frequencies that are log, okay? And use this g omega in order to solve this equation. Okay, we do this, we can make a change of variable called x to omega divided by lambda r, and then we have this, and now we have to solve this equation, and look that now what we only need is, again, the adjacency matrix, but now I don't need the set of natural frequencies, I just need the frequency distribution, okay? And this is an expression that I can use in order to get information about the synchronization threshold. In order to explore the synchronization threshold, as usual, take this approximation. So R is very, very small. So I can put here G0. I can solve this integral because it's analytical, and I have this expression. You see something here? How to solve it? Let me give you another hint. You see what's happened here? Let me give you another hint. But you are not a student. Yeah, it's an eigenvalue problem. Oh, the next guess was this one, okay? So I have to find a vector that gives me the synchronization around each node, that when I multiply this vector by this matrix, the result is the same vector multiplied by some scalar, by some number, okay? And the number is this one. So this is an eigenvalue problem, though. My solution is an eigenvector of the adjacency matrix. Okay, it's nice, right? Which eigenvector? I need that this lambda c is the minimum one, the minimum possible one. So the eigenvalue will be the largest, okay? So this is an eigenvector, and in fact is the largest eigenvector of A. So let me write this expression, and I have the first analytical, now yes, analytical expression for the critical coupling in the Kuramoto model on a network described by an adjacency matrix A. You see some similarities with our previous knowledge about the Kuramoto model? Yes, right? Look at this. In the Kuramoto model, in the usual Kuramoto model, this is the critical coupling. So now, the critical coupling in the network is the critical coupling of the Kuramoto model divided by the largest eigenvalue of matrix A. Which are the properties of the largest eigenvalue? Okay, we still don't know, okay? But we will know now in 5 minutes. Okay, this is, again, I repeat, I stress, this is the first analytical approximation of the critical coupling of the Kuramoto model. Okay, let's do another approximation, okay? We are on fire now. And let's do what's called the mean field approximation. And the mean field approximation is, in order to go further and try to make some more analytical results, let's assume that the synchronization around a node I is the global synchronization of the network times the degree of the node. Remember what Albert said? Okay, it was not normalized. Yes. Now, what I do is, yes, it's not normalized. In fact, the local synchronization is the global one times, which is a number between 0 and 1, times the connectivity of the node. Okay? It's harsh approximation. Okay, so I plug this here, and I obtain this equation. Okay, I obtain this equation. Now I make the sum across all the nodes of the two parts, A and I, okay? Let me put it in a separate way, like this one. And now I have to make the sum of the connectivities of all the nodes. And this is something that typically in networks, we use the continuous degree approximation. So in order, instead of summing across all the nodes, we sum across all the degree classes. We change these sums by integrals. Sorry. And we have this, okay? So we change this sum by this integral, and this sum by this integral, okay? And then, look what happened now. I now repeat the limit when r is going to 0, so I can put it g0. I put it outside. This is something that I can solve. It's pi divided by 2. And then I have this integral and this integral. And this integral is the average degree of the network. And this integral is the second moment of the degree distribution. So I have this result. In this case, the only thing I need to know is the frequency distribution in order to know this number and the degree distribution, because with the degree distribution, I know the first moment and the second moment. How it corresponds to the former result? There is a nice mathematical result that tells you that if you have a collection of networks, so a collection of matrices A's, with the same degree distribution, remember that a degree distribution can be fulfilled by a lot of networks, different networks, okay? Then, the average maximum eigenvalue of this collection of matrices is the second moment divided by the first moment, okay? So, taking this last result, and considering that the second moment of a scale-free network, of a very large heterogeneous network, tends to infinity when gamma is less than 3, because this integral tends to infinity when the gamma is less than 3, what happened is that the critical coupling in scale-free networks should vanish, should go to 0, because this number goes to infinity. Obviously, in real networks with a finite size, it's not infinity, but it's very, very large. So this means that if you have an heterogeneous network with a very large second moment of the degree distribution, the critical coupling of the Kuramoto model is really small compared to the one in the mean field Kuramoto model. And this is what numerically we observed. Remember when I showed you this. The more heterogeneous, so the larger this number is, the less is the critical coupling, okay? Okay, if you notice, we have done a lot of approximation, okay? This time average approximation leads to this equation, which is exact result, okay? So you can solve it analytically, you can solve it numerically. Obviously, there are behind a lot of approximations. Remember the error we have to remove because of this difference of scaling. Remember the nasty things about time averages, for instance, okay? But this is the first result that we have. Then here we assume that we change the set of node frequencies by the frequency distribution in order to have this expression. This is the first analytical expression we have. So here you don't have to do numerics, just take the adjacency matrix, compute the largest eigenvalue, and that's all. And finally, after considering the average across networks with the same degree distribution, we have this final result, which is also analytical and easy to interpret, okay? Because this is analytical but difficult to interpret because I don't have a brain prepared to calculate largest eigenvalues of matrices. But with this expression, I can really express what's happening in my system. And this is the result by Ichinomiya. This is the result that you would achieve with the continuous approximation, the one that I showed you at the beginning of the lesson, okay? Okay, this is how it works. This is a really super heterogeneous network. This is a real heterogeneous network. This is, okay, heterogeneous, but not that much. And this is a not heterogeneous network. And see the time average approximation. Obviously here, all the approximation works. So it's a very, despite we have used a lot of approximations, it works very well. It works really, really, really well. And the reason is that it works very well because, as I was discussing with Hilda, the approximations are not that bad when you are around hubs. And since hubs are ruling what's happening at the onset of synchronization, and we will see it numerically now, this approximation works very well, okay? In order to check it, let's do, a numerical check, and let's focus on a microscopic view, okay? So now we go to the computer, implement for some network the Kuramoto model, and see how this synchronization happens at the microscopic level, okay? In order to do this, we define this correlator, at the end is a correlator, in which we can measure the degree of dynamical coherence between pair of nodes that are connected, okay? What we do is just to integrate these different of phases across a time window which is large enough. So if they are completely synchronized, we have that this correlation is equal to 1. If these two are completely unsynchronized, they are not, they are incoherent, then we have that this is 0. And what we do? Take a real network, take the real network, put for some lambda the Kuramoto model, measure the degree of coherence between this link, and then what you have is a new network in which you have that some links are not present, like this one or this one, and some links are very well represented because they are very well the pairs of nodes that these links are joining are very well synchronized. It's the same as passing from the structural network to the functional network, okay? But with the constraint that we know the topology, okay? And if we do this, what we can do is to say, okay, I have a network, but which are the links that start to be synchronized for very low couplings? And if you do this, you have these two pictures. For Erdős-Rényi networks, and for a scale-free heterogeneous network. For a scale-free network, for Erdős-Rényi network, for homogeneous network, remember, what you have is that before the onset of synchronization, microclusters of synchronized nodes are formed, and at the onset of synchronization, what happens is that some of the clusters start to merge, and a giant component of synchronized nodes appear. Instead, in a scale-free graph, there is always a single synchronized component, this one, that start to grow, and grow. And these nodes, these little nodes that apparently have very low connectivity here, remember that this is functional connectivity, not a structural connectivity, these are the hubs. So the first ones in which the synchronization clusters nucleates, the first ones that start to grow these synchronization clusters are the hubs of this network. And that's why these approximations work very well in a heterogeneous network, okay? Okay, so now let me speak a little bit about the other way, the other side of the coin, and let's use the knowledge of how is the influence of a structure on dynamics in order to study how I can use the knowledge of a dynamical system or the dynamical response of a system in order to infer the structure that there is behind, okay? So I will talk about modular networks. Albert, do you remember this network? This is a network of collaboration in Spain, the FISES network. Because yesterday, Albert was making some merchandising about his software, so this network is made with his software. And, okay, this is a collaboration of Spanish researchers on statistical physics and nonlinear dynamics. And if you can see that there are communities, okay? Typically, networks are not only heterogeneous, they are heterogeneous, but are also shaped structure around modular structures, okay? So you have here one community, here another one, this is another one. Okay, I have not highlighted all the communities. The problem of community detection is very old, okay? As is an MP problem, because you don't know the number of communities, the size of each community is different in principle, so you have to check all the possible partitions, and you have a large network, it's impossible. I mean, you will take a non-polynomic time, okay? So there are a lot of solutions coming from classical clustering techniques, from computer science, optimization-based approach like the modularity one, which is one of the most famous, and in the last years, some techniques from Bayesian probability, so from inference, with block models, etc., have been developed in order to tackle this question. But this is a very, very important question that is not solved, okay? How to make a partition of a network in communities so that inside a community, the connectivity is very large compared to the connection of these nodes with the rest of the system, okay? Okay, so what happened? Well, and in the brain, obviously, this is something very important. Right? We are in a school and, that is associated to brain dynamics and brain structure, and obviously, the modular structure of the brain is very well associated with the segregation integration problem, in which you have to have heterogeneity, shortcuts, but also a modular structure in order to perform tasks, okay? Okay, so let's explore very simple community networks, as I was an algorithm introduced more than 20 years ago already. So it's a lot of time, in which we have this, you have these kind of structures. Here you have 4 communities, okay? And you see that the wiring inside each community is much larger than the wiring of these nodes with the rest of the system, okay? So we have this synthetic, we have a connectivity of the nodes here inside each community, and also another connectivity for the nodes with the rest of the other nodes in the other communities. And this is a hierarchy, and you can construct with this a hierarchical model in which you don't have only this, but you have now again 4, and you have also this connectivity. And this connectivity, this wiring is much smaller or much weaker than the wiring here and the wiring here, okay? So you have a much larger wiring here inside these small communities, then a medium wiring inside these communities, and the weakest wiring joining these 4 communities, okay? This is a hierarchical modular network that you can use in order to study what happened in the synchronization of the Kuramoto model in this kind of topologies. Topologies in the sense of structure, not mathematical term, okay? Okay, so let's explore what happened with network with more than 200 nodes, 16 small communities like this, and this, and 4 supermodules, okay? And then the network, which is the whole level. So the connectivity of each node is shared among the levels. So we have K1, which is the connectivity of the nodes inside the microclusters, K2, which is inside this medium cluster, and finally K3, which is across the whole network. Typically, we use this scheme, 15 for K1, 2 for K2, and 1 for K3, or 13 for 1. You see that the sum in all the cases is 18. So each node on the network have 18 neighbors. In this case, 15 with the first level, 2 with the second level, and 1 with the macroscopic level. And this is what happened with the synchronization. Okay. nothing more, nothing less, okay? But let's see what happened at the microscopic level, and let's call again the correlator between the nodes, so we can measure how the local synchronization between two nodes, I and J, evolves as a function of lambda, as a function of the coupling. And we have these kind of pictures, very, very similar to the ones Albert saw yesterday. And for these couplings, we have these correlations. And as you see, everything starts at the microscopic level. The microscopic level starts to be more synchronized. Now you have something at the medium level. You can see better here. You can have something at the medium level. In this medium level, there is no a large synchronization compared to this one or to this one. Then the second level starts to emerge. And finally, you have the adjacency matrix, because everything is synchronized when you are here, okay? So at the end, what you have is that the functional network corresponds to the structural one, because all the links in the real network are well synchronized. And if you study what happened at the level of each link, so level 1, here, level 2, and level 3 in the global network, you see a nice phenomenon, which is this minimum. And this minimum tells you that in order to achieve synchronization in the microscopic level, you need to start or lose some kind of synchronization at the global level that then you will again recover when you increase lambda. So in this minimum, you see what happened at the different hierarchies at the different level, okay? First level synchronized, second level synchronized, and third level synchronized, but in the path to this synchronization, you have an interplay between what you synchronize at one level and what you have to lose at the other level, because at the end, you need to incorporate the strength of the coupling in a clever way, okay? Okay, and now the question that was addressed in this paper by Alex Arenas, Albert Diaz-Guilera, and Conrad Pérez Vicente is, what happens if I don't know the network? I don't know the network, but I know what happened at the level of modules because I have learned what happened just now. So let's take the Kuramoto model, but in a simplified version in which all the frequencies are the same, are identical, okay? In this case, you always find synchronization because you always, well, depending on the structure, but typically you always find synchronization if you wait long enough, because all the frequencies at the end are the same, okay? So in this case, what they found is that in the trajectory in time towards synchronization, this is the synchronized state and this is the synchronized state, you see the modules. Here, synchronization at the level of nodes. Here at the first level of communities. Here at the second level of communities, and finally at the level of the structure. And you see that this plateau and this plateau are completely different because we have here a 13 and here we have a 15. In this case, this plateau is larger because the wiring here is much stronger than in this case. So you spend more time at the first level of communities, so you can infer which is the organization that you don't know, remember that you don't know this, by just looking at this. But what is magic is that if you compare with the ranking of eigenvalues of the Laplacian, you obtain a similar picture. So you not only qualitatively know how is the modular structure of your network, but you also quantitatively can recover the spectral structure of here the Laplacian, which is a matrix capturing the structure of the network, okay? Okay, and finally, let me talk about one application to sign networks, because community detection in sign networks is even more difficult, okay? In sign networks, typically, a community is defined by the fact that if you have a community here, all the nodes share positive links. Here is another community, and here the nodes share all positive links, but the links with the nodes in other communities are negative, okay? This is the definition of communities in a sign network. And this is very important in order to analyze, for instance, social networks in which you have friendship and foes, okay? So what we can do is, okay, if we know that in a modular network, the Kuramoto model tells us the structure of the communities, let's consider the Kuramoto model in sync networks in order to see what happened with the real structure. This is the version of the Kuramoto model on sync networks. Here you have an adjacency matrix capturing the positive relations. Here you have a different adjacency matrix capturing the negative relations. Look that the sign has been interchanged because here are negative interactions, okay? And then you have the coupling between nodes according to the sign. Attractive and repulsive, okay? In the Kuramoto model with positive sign, typically, two nodes try to be at the same phase. In the Kuramoto model with negative interaction, you try to be at the maximum possible distance, so it's pi, okay? A difference in the angle of pi. Okay, so we construct, again, a network which is synthetic. We have only two modules of the same size. We have an all-to-all connectivity here, an all-to-all connectivity here, and positive links. And we have a wiring between communities that is tuned by this parameter P. P is the probability that two nodes belonging to A and B respectively are joined, obviously, by a negative link, okay? So if you do this, because of this symmetry, and you can check the calculations here, because now the calculations are really, really close to the usual Kuramoto model, you can change this equation by this one. Again, Homer Simpson comes and say, okay, this is a very nice equation, and we can try to derive exact results. And in fact, using the degree of synchronization in each population, so this is the degree of synchronization at here or here, depending on alpha. You can transform the equation in the typical one we know how to tackle, and okay, after some analytical calculations, you have this result. This result is really nice because, look, tells you that the critical coupling decreases with the number of negative interactions. So, if I have this population and this population completely isolated, so no negative interaction appear, the critical coupling is this one. When I start to add negative interactions, because P is not 0, then the synchronization shows up before. Look, P0, P1. And this is what happened in real life. If I have a friend and we have a common foe, we get closer. It's the same, okay? It's something that apparently is counterintuitive, but it's not counterintuitive. At the end, the repulsion of a common enemy make us being closer, okay? And this is numerics, and this is analytics, so it works very well. Okay, so what we have learned, and I'm finishing now, is that if I have so to say, ideal scenario in which I have two communities, the Kuramoto model allows me, by monitoring the cloud of synchronization, to unveil that really there are two communities that are repelling each other, okay? So if I don't know what's happening inside, by looking at this diagram, I can observe, I can have some clues about what is the structure, in particular, what is the balance of the network, which is the important thing. And this is what we do in order to tackle the analysis of a sign network, which has to do with the an ecological network of plants in semi-arid system. This is Monegros Desert that you know very well. This is the Cabo de Gata in Almeria, another desert in Spain, in which you have a lot of plants. And they are competing because the resources are very scarce. So these are really interesting systems for community ecology, because the resources are so scarce that there are a lot of competition and also a lot of collaboration between species, so to say. So with the help of ecologists, we measure the balance of the relation with plants, and we see that in these cases, the balance, those triads, sorry, that are balanced were very well represented with respect to the random case, while those triads that are not balanced are underrepresented with respect to the random case, meaning that balance, as a theory, works at least in this kind of plans. The problem is that you don't only find triads, you have networks, and this is a typical network with negative and positive interactions among species in the system, okay? And the thing is, what the hell is happening here? Which are the communities? This is not the ideal case in which you have two communities with positive here interactions and negative here in between. You have to see what is the best structure that describes in a coarse-grained way this real network. Okay, put the Kuramoto model, and let's see what happened. And what happened is that it differentiates 10 groups. One group, this one is the node 1, which is a very important species with all these plants, okay? In the representation, I have highlighted this. And then there is a, sorry to say, merde, of clusters here because there is no perfect balance, okay? But looking at what's happening here, we can check that there is a species here that if we remove it, we pass from a situation in which there are not well-defined clusters to a situation in which we have less clusters. We pass from here from 6 to 3, and they are very well separated. So you can say, well, these plants and these plants repel each other for sure. These plants and these plants repel each other for sure, and this as well. And these are repelling them, okay? So you get a coarse-grained picture about the organization of the balance in your network just putting the Kuramoto model in same networks here, okay? You have, looking just the unit circle, you know how they are organized and how to, most importantly, how to intervene in the network, like here, to remove, okay, in plants it's difficult, but in a social network it's not so difficult. If I want to remove one guy because the balance in the classroom or in the office will be better, okay? And this is an important thing because clustering inside networks is a very hot topic. Last week I was in a PhD thesis about just this. And I asked, okay, you know how the Kuramoto model can solve a lot of questions? No, I don't know. Okay, obviously, from the mathematical point of view, it's qualitatively. It's not quantitative. I mean, it's not something rigorous. I mean, it's not a rigorous proof. But, you see, Kuramoto model can help you, not because you know how the response of a system is, and then you can use this knowledge in order to know or learn how the structure of a system is from the dynamical functioning, okay? So I'm finishing here, and as I said, for tomorrow, we left the third level. We have gone from a structure to dynamics, we have gone from dynamics to structure, and finally, tomorrow, we will couple structure and dynamics and tackle adaptive networks and explosive synchronization, okay? Thank you very much.
Thanks, Jesus, for this wonderful lesson. Is there any question, comments? Come on, don't be shy. No, probably you are already.
They need coffee, and me as well.
Yes, okay. So we have half an hour, Ila, for the coffee break. So let's go to the coffee break. We can discuss those who have particular questions or they want to talk with Jesus. It's the moment.